Hi, my name is Brady Peterson. I'm here to do a quick overview of polyalkyl thiophenes, and more specifically poly-3-alkyl thiophenes, as they relate to electrically conductive polymers. A brief history and background of these materials starts with conductive polymers in general, with polyaniline first described in the mid-19th century, followed by polypyrols and polyacetylenes in 1963, and salts of tetrahydrofolvaline in the 1970s. The earliest research publications pertaining to polythiophene surfaced in 1981, while a Nobel Prize was awarded in 2000 for the discovery and development of conductive polymers. McCullough and Reike undertook mechanistic studies for polythiophene polymerization, while Collard studied structural isomers, including poly-3-perfluorooctyl thiophene derivatives. Research focused on alkyl group substitution at the 3 position of the thiophene ring and subsequent conferred properties. Synthesis methods of these polythiophene materials include oxidative polymerization methods, which include chemical oxidation as well as electrochemical oxidation. These methods offer less control over polymer structural motif and are less common in general. There are also advanced chemical methods which yield greater monomer selection and greater control over polymer structural motif, where 100% regioregularity can be achieved. McCullough and Grignard metathesis methods and Reike methods are included in these advanced chemical methods. Here is shown a general overview of the mechanisms associated with oxidative polymerization methods. On the left can be seen a schematic for the electron removal from thiophene to form the dimer of thiophene and subsequently the polymer of polythiophene. On the right is shown chemically aided oxidation with iron 3+ going to iron 2+. Here can be seen the general mechanisms for the advanced chemical methods for synthesizing polythiophene polymers. On the left can be seen the McCullough and/or Grignard metathesis methods, and on the right or lower right, the Reike method. Both methods use either magnesium 2+ or zinc 2+ to activate thiophene prior to coupling using 1,3-bis diphenylphosphenylpropane dichloronickel 2 or 1,2-bis diphenylphosphenoethane dichloronickel 2, after which a reductive elimination yields either a dimer or, upon continuing this reaction mechanism, the polymer polythiophene itself. There are 3 manners in which the thiophene monomers can combine to form polythiophene polymers: head-to-tail, head-to-head, or tail-to-tail. Extended pi systems within these polymers due to p orbital overlap in coplanar thiophene repeat units confers electron delocalization, which then facilitates electrical conductivity along the P3AT backbone after doping. Upon doping, different properties arise, such as electro, iono, and thermochromism. There is also the possibility of 3-alkyl substitution, which then itself alters different properties within these polymers. Alkyl chains longer than C4 are both solution and melt processable, which exhibit good solubility at room temperature in common organic solvents and are easily processed into uniform and flexible films via solution casting or spin coating. These polymers are made conducting via doping, where doping can be accomplished either in solution or in vapor phase. These polymers that are doped can also be processed similarly to non-doped films. Polythiophene polymers can be processed by various means, including conferring water solubility via functionalization of the 3-alkyl substituents, or via supercritical carbon dioxide, and through incapping illegal thiophene chains with thermally labile alkyl esters to facilitate casting thin films from solution. Many P3AT materials are in their research phase and are offered on small scale, such as gram quantities, through companies such as Sigma Aldrich or Reike Metals Incorporated, or are produced in laboratories in small batches for research purposes. Such derivatives such as 3,4-ethylene dioxythiophene can be and are produced on ton scale for applications as anti-static films in electronic consumer products. Polyalkyl thiophene polymers have found many interesting applications, such as in optoelectronic devices, electrochromic devices, rechargeable battery electrodes, organic-based field effect transistors, anti-static surfaces, flexible transparent displays, and supercapacitors. As can be seen on the lower left is a video of an electrochromic film of polyalkyl thiophenes, where redox cycles show differences in opacity depending on which potential is applied.